Lecture 3, Part 3. So before we continue with the multi-layer neural network gradient descent, I want to show you a website that I forgot to talk about in the previous two parts. So it's the neural network link, and if you click on the link, you can see this neural network that you can play with. And it's a simple one at the moment. You have two inputs, x1 and x2, and you have two hidden layers, one with 4 units and the other one with 2 units. And this is the training data set, and the classification will be shown when after we play with this. And you can change the learning rate. So right now 0.03 seems okay. And you can change the activation as well. So the one that we went through gradient descent, that we actually calculated the gradient is for sigmoid activation. So we'll use this here. And we also briefly talked about ReLU, the rectified linear units, and the hyperbolic tangent. And the linear one is just LTU. So you can play with these. And we haven't talked about regularization yet. We will do it in lecture 4. And leave the problem type as classification. We're not doing regression. So if you click start, it will take a while to classify stuff correctly. And you can play with some of the other things. We haven't talked about batch size yet. We will next lecture as well. Okay, so it seems it's doing something. And okay, so I'll stop here. So after around 600-700 iterations, we get the classification boundary like this. So first it's not a line, and it's classifying all the training data correctly. So the inside is blue, the outside is orange. And if you look at the weights, the orange weights are the negative weights. The thicker orange line are the ones with higher weights, and similar for the blue ones, these are thicker, and blue ones are positive and orange ones are negative. And you can see actually what each unit is doing. So this unit is a logistic unit, so it's classifying the left half as blue, the right half as white. So I think it's using blue and white instead of blue and orange. But basically each one is linear, but when you combine them, you get something like not so linear, and you combine all of them, you get something that's like this. So it works great, but it's kind of slow. So it takes almost like 1,000 iterations. If you want things to go faster, you can try ReLU, and if you click run, it'll be like instant. But the classification boundary is like multiple straight lines, and it's not that good, but it's okay. It's classifying everything correctly already. So, and it's only taking like 39-40 iterations, so it's really fast. And also you can play with other data sets. This one is the one that we talked about, the exclusive OR. It's just there are some randomness, and this is the separable one. It's very simple. And this one is usually the hardest one. So using ReLU, it's actually also difficult to get this correct. So we should maybe add more. Let's add more units and see if it works. Note that we are using ReLU, so it should be very fast. It's not great, but it's fast. Well, it's doing something. So it's trying to get somewhere, but it seems it's hard because the number of linear pieces is not enough to capture everything. Okay, I think it's kind of stable and it's not working. So you can play with different structures. You can add more layers, add more units, and sometimes it may be able to classify every point correctly, but it's going to be hard. In any case, you can play with this and talk about it in math homework number 3, and you can share your findings on a Piazza post that I haven't made yet, but I will. So let's stop this and let's get back to the mathematics. Okay, so in the previous part, we talked about a one hidden layer network, and we went through taking the derivatives. So we want to know if we can do the same thing if we have more layers. The answer is mostly, but there are some changes that are needed. So we need the superscripts, that's the first thing. And let's just use a simple one with only 2 units in each layer. This is layer number 2, unit 1, layer 2, unit 2, and everything gets connected with A. So, and our cost function. So suppose we want to find the same weight. This is called 2, 1, 1. So the derivative we want is weight 2, 1, and 1. And it seems using our old logic, backwards, 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 and backwards. So DC, DA, 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 1, 2, DA, 1, 2, DA, 1, 1, and DA, 1, 1, DW2, 1, 1. Okay, so that seems to be the answer, and it's wrong. So why? It's because we can go this, 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 and this. So there's another path. So when you use chain rule, you need to add all possible paths. So the other path is DA2 to A2 to A1, 1, A1, 1, 2, 1, 1. Okay, so it looks simple, but there are only 2 units and there are only 2 hidden layers. So if you have like 157 layers, then this is still hard to do. So it's hard to list all possible paths. That's the first thing. How to implement that, that's one. And also it's kind of very computationally expensive if we want to recompute the same parts like multiple times. So we may be able to save some work if we store the value from the previous weight derivative calculations. So that's what we'll do next. As you can guess, it will involve induction and a lot of mathematics and basically a whole page of notations. So if you are not interested in this, you can stop here. And I will not put any questions like this on the homework on the exams, and you will not be asked to implement this for the programming assignments. So you are okay if you miss this part. However, if you want to know the answer, like how to actually implement multi-layer neural network, and also if you want to learn about the delta notation that may be used in future courses like 760, we can continue. So again, if you are not interested in the mathematics or you feel that this lecture is boring enough already, so you can just stop here. And otherwise, if you haven't closed this video yet, let's get back to the mathematics. Okay, so we want to start with a very general unit, J's unit of layer L-1. So what is this connected to? Connected to many activation nodes in layer L-2. Let's use J prime. Suppose we are interested in one particular weight, that's J prime J L-1. It seems these units are not relevant, so let's just get rid of them. We don't need anything that's not relevant. And on the other side, it's connected obviously to the same unit, the activation. And this side, there are lots and lots of stuff again. And in general, it's some kind of J prime prime in layer L. And these two are connected by the function g, and these two are connected by the weights j prime prime l. Okay. So for the other units, you just have different j prime prime. So I'll not write all of them down. Okay. So what we want to do here is, suppose we know the derivative with respect to the next layer weights. We want to find the derivative with respect to the previous layer weights in terms of that. Then we can save a lot of work, and we can do this like systematically. So let's write it down in the form of an induction. So assume we know this dc dwj j prime prime l. What we want is we want to write, okay, I actually put the L on top of C. That's not good. And we want this j prime j L minus 1. So if we can write this as a function of that, then it would be great. Unfortunately, no. So we need to write this as something else and write this also as something else. So it turns out that this can be written as some delta. So as I mentioned, there's a delta notation multiplied by the activation. The reason why this is true is you can actually write it out. So this is just derivative with respect to z j prime prime l and z prime prime l with respect to w j j prime prime l. Right? So if you look at this part carefully, this part is this linear combination of the a's and w's differentiated with respect to this w. So of course it's just a, so it's that part. And this part we don't know, it's something that we calculated before. We just call it delta. So now our goal becomes, so hopefully equals to a lot of work, we can get the same form a j prime l minus 2. And the goal is to figure out what this delta formula is in terms of the previous delta, so we can calculate this recursively. And you just, after that, you just multiply it by a. And let's actually do the algebra. So we need the chain rule. dc, we have this z thing already, l, and it's actually the same as before. We're just using more complicated notations. So AJL minus 1 and AJL minus 1, AZJL minus 1, and are we doing the right thing? ZJL minus 1 and WJ prime JL minus 1. So it's going back, going back, going back. There must be something wrong because this looks like still a train. As we talked about before, we have all of these things. So all of these paths can go back here and go back here. So we need to add them up, right? So important thing that I forgot, j prime prime starting from 1 to the number of units in this layer. The notation is ml. Okay, so now we have the correct expression. Let's simplify this somehow. So this is our sum j prime prime from 1 to ml. dc dz, we already defined it to be delta, so now we can use it. And z with respect to a. So it's this with respect to that, so it's just the weight. So it's wj j prime l. And a with respect to z is just this g function. Remember, g prime for logistic regression, for logistic activation function, it's just a 1 minus a. So it's just a l 1 minus a. Okay, and we have one term left, z with respect to w. So this z with respect to w, again, z is a linear combination, so the derivative is just a. So we have our aj prime l minus 2. Okay, great, because aj prime l minus 2 is this part. So we do have a recursive expression for delta. This is our delta formula in terms of the other deltas in the next layer. So what we can do is the last layer delta. So the last layer, we can calculate the delta explicitly by differentiating the cost function. And in the previous one, we use this formula to calculate the previous layer delta and the previous layer delta and so on in terms of the deltas we already calculated. And at the end, we just multiply these by the a's. So that's how we get all of these derivatives. So it seems it's kind of messy here, so I actually typed it up. So this is just a general notation, and I'm writing out all the deltas here. So the last layer delta is just the derivative of the cost function. Here the cost is the square error loss. And this one is exactly the same as we derived. It's just we are using L and L minus 1. Here's L plus 1 and L. And these formulas are the same as what we did derive. We didn't talk about the bias terms. The bias term is just when the activation is 1. We have the bias term derivatives. So they have the same formula, that's why. And you still do the same thing. You still subtract learning rate multiplied by the derivative. So the process is exactly the same. It's just the delta formula helps you to calculate these things recursively and save some computation. So that's all I want to talk about in this lecture. There are lots of other interesting things about neural network. We will talk about some of them in lecture 4 and more complicated network structures in like lecture in 2 or 3 weeks.